looks like everyone survived the storm. And we managed to make it through that incredibly gray day that we had on Monday. Knocked over a branch. But anyway, so hopefully you guys did enjoy a little bit of a break there. I know we haven't had any semesters been going straight through, right? So I'm sure any time off is appreciated. But hopefully you guys got a chance to watch through the video that I posted there, or at least followed one of the links that we have there about MO theory. We're going to just kind of wrap up some thoughts about MO theory today, and then we'll go into chapter 10, which will be the last chapter that we go through. So we've got, only about a week and a half before Thanksgiving, right? So everyone's got their plans going here, so stick with me. We just got a little bit more to do, and then we'll wrap up this semester, and we'll go on to Gen Chem 2, right? No. Like that, I'm good. I'm done. But anyway, so what advice or not advice? You guys are all done with registration then too? Is that you're gonna have to go fight in line to, for the 10 spots that are in the class that you need? But anyway, so busy week so far is what it is. But so let's get started with prayer, and then we'll launch back into chapter 9 here. But Lord, we just do thank you, Lord. We thank you for the protection that you've given us from the hurricane and from the weather and all these kind of things, Lord. And we just know that everything is a blessing from you, and we just pray that we be good stewards of those blessings, Lord. Just help guide our hearts to seek after the things that you would have us seek after, and just help us to use everything that we have for your glory, Lord. Just keep the distractions from us, Lord, and keep our mind and our hearts focused on you and the things that you'd have us focus on. And we just ask this all in your name. Amen. All right. So, we finished up, or in that video there for you guys. I know I was going kind of fast through it all, but hopefully you guys had a chance to watch through it and take the notes that you needed to. Basically, what we got to is how do we construct, how do we build, and how do we read and interpret these MO diagrams. And what I wanted to do is just kind of talk to you guys a little bit about some of the, I don't know, what's the word I want to use here? Subtleties or differences or pros or the cons, or why in the hell would we even want to do this to begin with, kind of thing, right? So that's really what I wanted to do today. So, but before we get to that, I wanted to give you guys just a couple of quick problems here for you guys to go through. So I have a question for you. I want you guys to tell me the bond order for carbon monoxide. So tell me the bond order for carbon monoxide, CO. Tell me how many sigma and how many pi bonds there are. Okay? Carbon monoxide. And you'll need that, right? You'll need the MO diagram there. So if you have your books or your notes or whatever you might need.
the octet rule?
Do carbon and oxygen? Yeah.
I thought they did.
Yes, they do.
Thank you.
Mm-hmm.
Maybe this part, do your thingy, your magic circles,
Mm-hmm.
you get a weird chart. And then you keep 0 and 0, so you go all the way up that way.
Oh, you're following the okay.
This one, but if I do it this way, I do not. But,
But you're not following the octet rule.
yeah,
Right.
then you get your zeros.
Okay.
You follow the octet rule over the zeros for these ones, which is fine, that's all it is. I just think it's funny.
Mm. Yeah, like I said, you're not gonna have a situation like that though, right?
Yes.
Yeah.
Okay.
All right, so what's step one for a question like this?
The little structure.
Hmm.
No. Oh wait. I guess you're right.
Step one. That's the first step I did in the examples I walked through in the video with you guys.
Put it in that thing.
Okay, what did I put in there?
You got your things. And you
My things. I put my things in my things. All right, step one. What do we mean, Gabe?
You have an atom or an element over here and an element over here, and you put your electrons.
Aha. So what do I fill into my MO diagram? Electrons. Remember, MO stands for molecular orbitals, right? What lives in orbitals? Electrons. Got it? Okay. So what electrons live in there? Valence electrons. So what's step number one?
Getting the valence electrons.
Figure out your valence electrons, right? All right. So there we go. How many of you guys watched the video I posted on Monday? 1, 2, 3, 4, 5, 6, 7. 7 of you guys. Cool. Awesome. So, you guys are gonna have some catching up to do, okay? Just because you don't wanna watch the video, or you don't wanna do this, or you don't wanna be here, or it's too early, we had the day off, whatever it might be, doesn't mean that the material isn't there, doesn't show up on the exam, right? So whatever, I'm not here to force you guys to do something or anything, right? But you guys sign up for a class, these are the circumstances that we have, and the expectations are either that you guys follow along, or read through the book, or follow whatever lecture that you guys need to get the material done, right? That's what the expectations are. If you guys aren't meeting the basics, then that's gonna be trouble, okay? So, MO theory, right? We gotta get our valence electrons. Remember, we're limiting these to diatomics, right? So we have a very simplified version of our diagrams. But as with most things that we've talked about in general chemistry here, right, we're gonna be dealing with our valence electrons, okay? And so the job is to tell us where, right, this is one of the pros of MO theory, is like, where do the electrons actually live? In what orbitals in the molecules that they form, right? And so we need to know the valence electrons for these things. So Gabe kind of mentioned it here, but let's see what everyone else remembers. So there are 3 parts here. Right, there are basically 3 parts here to any MO diagram that we'll deal with. Right, the left, the middle, and the right. What are those three parts? What do they represent? What do you mean?
So like the electrons that fill the orbitals per atom. So like on the left side is one atom, the right side is one orbitals when they're together.
Good. So the left and the right hand side represent the atomic orbitals. Okay? For the individual atoms that we're going to be putting together to make something new. Okay? Now you guys should already know that, because how are those orbitals labeled on the left and the right hand side?
Atomic orbital.
Yeah, right? How else do we know that they're atomic orbitals?
They have 3p and 1.
What are S and P and D and F orbitals? They are orbitals that exist on atoms, right? As soon as we start to make bonds with things, we don't have atomic orbitals anymore, we have molecular orbitals. We've got our purple paint, right? We've got our hybrid orbitals that need to come together to generate the different geometries that we have, okay? So basically the left and the right hand side here, if you want to think about it in a way, right? These are just different paint buckets that we're going to mix together to make something new, right? These are the things that we come together to form bonds in our molecules. Got it? So what's step one?
Figure out valence electrons.
Valence electrons for each of the atoms that are in there. Got it? So I asked you guys to do that mode diagram for carbon monoxide. So pick one side for your carbon, pick one side for your oxygen, and fill in your electrons. Okay? Green doesn't show up too well, does it? Yeah, maybe. I don't know what else I could really do, but hopefully you guys get the point, right? We found our valence electrons in either side there. Great. So there's our atomic orbitals. Okay. So now we know what the left and the right is. What's the middle? Well, the middle is labeled with what? Sigma, pi, got these little asterisks there, this kind of stuff. What's all that jumble of nonsense mean? What does a sigma mean? Yeah.
That's the strongest bond. There's always one of them. And yeah, is that correct?
Partially, right? So a sigma bond is always the first bond that gets formed. Okay. Now, what have we typically been drawing as our first bonds? What's step 2 in our Lewis structure construction? Step 1 is get valence electrons, right? Step 2 is draw our skeletal structure, right? How do we draw a skeletal structure? Draw a single bond between everything, right? Is that how it works? So what's a sigma bond? Well, a sigma bond is the first bond that's formed between any two atoms, right? There are single bonds. Great. Now, what else do we know about our sigma bonds? So Gabe mentioned that they're usually our strongest bonds. I would agree with that.
Why would you agree with that?
Why?
Isn't it, if pi bonds are present, aren't they closer together than they normally would be? So they're harder to
So
break?
hang on to that thought. Hang on to that thought. What else do we know about sigma bonds? Give you a hint. It's later on in your notes. What's up?
There's always a sigma bond.
There always are sigma bonds, yes. Anytime you form a bond, you're gonna have to do that first, correct? Yeah,
There are those like head-to-head bonds.
correct, right? Whenever we form a bond, it's basically a head-on collision between orbitals, okay? Sigma bonds are no different, they're a head-to-head overlap of our orbitals. Which means what? So it's one of these little subtle points, but it's definitely in the end of your slides there. You guys have those. Some of the pretty pictures that come out of the orbitals discussion when you guys are going through this. That slide right there. Where do we find the electrons in a sigma bond? Where are they located in space?
You know, S orbitals.
There are s orbitals. They can be there. Right? Give you guys a hint. Okay. So let's draw a just standard single bond in between things. Right. What does that mean to us? It means that we've got two atoms that are bound together, right? And those electrons are holding those things together, right?
Oh.
So where, we would call that a sigma bond, right? A single bond. Where are those electrons hanging out? Where are the orbitals? Well, hang on to that thought too, but.
They're in between the atoms.
Exactly, right? So our sigma bond density, where those electrons are hanging out directly in the plane of the atoms, right? They are between the atoms themselves. Now, why am I bothering to tell you that? Well, the next question in our series I'm going to ask you is if we're not dealing with sigma bonds, we're dealing with pi bonds, okay? But it's important to recognize that sigma bonds are the first bonds that are formed. They're always going to be present. It means the electrons are hanging out in between the two atoms. Right? Sigma bonds on their own tend to be stronger than pi bonds, but we'll come back to this idea that Andy asked there, or hey, wait a minute, right? You said something different earlier. Okay? So all that stuff's important to recognize. Cool. All right. So, now so what's the little star thing mean there on these MO diagrams?
Antibonds.
Antibonds, right? Now what in the world is an antibond? I'll give you a hint. It's like a bond, but anti, right? So what in the world is going on with antibonds here? So remember the name of the game is garbage in, garbage out, right? So if you take a look at the diagrams, we've got an orbital, we've got another orbital. So if I put two orbitals together to make a bond, how many orbitals have to come out? 2 in and 2 out. Okay? Now something that we haven't talked about as much is that we have different phases of the, how do I want to put this? Different phases for how the orbitals exist mathematically. Remember, the shape of our orbitals were all just based off of some graphical function, right? And that graph can go from the positive to the negative end. If you take a look in the book, you see that they shade them red and blue or orange and white, or right? They have different color for these orbitals. That's not arbitrary. That's representing the different phases that the orbitals exist in. Okay? So think about it like this. For half the time, the orbital can be plus, and half the time the orbital can be minus. Okay? So if a plus orbital interacts with another plus orbital, we get a nice bond, things can overlap, right? The two functions add together. Make sense? Right? So we have x plus x makes 2x. But because of math, we can have a situation where x and minus x come together. And what happens if you add those two? You end up with 0, right? The opposite. And so a bond and an antibond are just a consequence of the description of the math to get those orbitals together. You're like, that doesn't make any sense. You're like, yeah, I can understand that. But here's the point that I want you guys to think about. Here's what I want you guys to understand. Whenever you make a bond, there is also the exact opposite anti-bonding combination that gets made, okay? And an anti-bonding combination is exactly what it sounds like. It negates its corresponding bond, or it negates a bonding combination, okay? Because if you put 2 in, we have to get 2 out. All right, so that's what the little star is here, right? And you can see that these are all connected with these dotted lines that represent what orbitals went in to make those to begin with, okay? All right, so we got all this figured out down here. All right, moving on up. Pi bonds, what do we know?
They're like double and triple bonds.
What do you mean?
The amount of, so if it's double, you have a sigma and a pi. If it's triple, you have 2 pi and sig.
Mm-hmm. So pi bonds are what we've been representing as double or triple bonds. Not the actual double, well, let me see if I can find a better way of drawing this, okay? So back to the example we just had here, right? So I have a sigma bond that forms, that's the first bond that forms, okay? A pi bond, okay, is the second bond that gets formed, all right? A pi bond doesn't represent a double bond, it represents the second bond in a double bond, if you want to think about it like that. A sigma always has to be present, okay? And so just like what Andy was saying is when we've been drawing double bonds, we have a sigma plus a pi bond. If we have a triple bond, we have a sigma and 2 pi bonds. Got it? All right, so what else do we know about pi bonds? So if sigma bonds live in between the 2 atoms, where do the electrons in a pi bond live?
So it could be like some magical side-by-side thing.
Right? They form from the side-on overlap of unhybridized p orbitals. Extremely important. Do you guys catch that? What's the extremely important part about what I just said? They're from the side-on overlap, not too important, of unhybridized p orbitals. You guys catch me on this one? So write that down or keep it in your mind or whatever you want to say, but I'm going to come back and ask you a question about that in just a minute, okay? So where do pi bonds live? Sigma live in between the atoms, pi bonds live
On the side.
on the side.
Hamburger bonds.
Hmm?
They're the hamburger.
They're the hamburger buns, right? They live above and below the plane of the atoms, okay? Why am I bothering to tell you guys this? Well, I need to give you guys a lot of information, right? So that I can ask really complex questions. Make sure that you guys miss enough points, right? Otherwise, everything's too nice and easy. Now, okay, what does chemistry? Electrons. Do you think that pi bonds react differently than sigma bonds do? Absolutely. And part of that is because of where those electrons are living to begin with. Okay? If you live above and below the plane of the atoms, you're going to behave very differently than if you live in between the atoms themselves. It's an important idea that we're going to come back to again and again and again, especially for you guys moving on to organic at some point. Okay? Extremely important idea there. All right. So we got the sigma, we got that taken care of, we got the star, now we know what the pi's are, and we got all that kind of stuff there. Great, so now we got the basic construction of an MO diagram. Okay? Cool. So, back to the question that I asked. What is the bond order for carbon monoxide, CO? So we got our valence electron count, okay? We filled in our valence electrons for the individual atoms. What's the next step? Now we know what goes to the atoms. What do you think we have to do next?
Fill in your boxes.
Okay, now we got to fill in the molecular orbitals. So now we got the individual atoms. We're bringing them together to make our bonds. So fill them in. Do you have a question though, Gabe?
No, you asked what the bond order was.
Oh, yeah. So hang on to that for just a second. I'll get your answer here in just a second. how do electrons behave in life? The way I always think about it is electrons are lazy, right? They always want to go to the lowest energy that they can. But you guys already knew that, right? How do we fill in electrons on the periodic table? Do we start at the 7s orbital? No, we start at the 1s orbital. Why? It's the lowest energy, it's closest to the nucleus, right? So if you take a look, right, on the left-hand side, I didn't just add this in there for reference, right? Energy increases from from bottom to top. So when you fill in electrons in your MO diagram, where do you start? At the lowest energy, right? So just like building a house, right? You start to fill in electrons at the bottom. Now, MO diagrams are confusing. They're weird. Hybridization and geometries and hybridized and pluses and minuses, all this kind of stuff. Okay? At the end of the day, we're still dealing with an orbital. What's the maximum amount of electrons that can fit into any orbital in the entire universe? 2. Right? So even though this is scary and complex and there's weird things with it, how many electrons fit into there? 2. Okay, that's it. 1 up, 1 down, right? Okay? You guys with me? What happens next? Now we get a set of orbitals at the same energy, degenerate orbitals. How do we fill in electrons at degenerate orbitals? Well, put them in their separate apartments first, and then come back and pair them up, right? Good? Hund's rule and the Pauli exclusion principle and all that kind of stuff is still at play here. Electrons are electrons. So I start out with 10, 2, 4, 6, 8, 10 electrons there, okay? So step 1, valence electrons. Step 2, fill those into your MO diagram. Step 3 is assess what you actually did, right? So work our way from the bottom to the top. So we filled in 2 electrons to make a sigma bond. Cool. We filled in 2 electrons to make a sigma star bond. So what essentially does this mean here? We made a bond, and then the next set of electrons undid it, right? Okay. Moving up here, now we've got a sigma, and we filled in 2 of our pi bonds there. You guys with me? So, from our MO diagram, what types of bonds should be present in our structure? Well, we made a sigma, and then it disappeared, right, or got broken. And we made another sigma. Is this one canceled out by anything? No, so should we have a sigma bond present? Yes. Are you ever going to have a sigma bond not present? No. No, not unless there's something weird going on, right? We made 2 of our pi bonds, or any of those canceled out? No. So what does this tell us? We should have 1 sigma and 2 pi bonds. What does that translate to in our heads? A triple bond, right? Now, did you guys draw the Lewis structure for carbon monoxide?
Yeah.
What did you guys draw in your Lewis structure?
2 electrons and octets in the triple bond of carbon and 2 more electrons.
Right. So if you guys were drawing this here, right, hopefully you come up with something like this, right? So does our Lewis structure match the information in our MO diagram? Yeah, right? We have 1 sigma, 2 pi bonds, right? And we might think that these 2 right here represent the orbital, the lone pairs that are sitting there in our sigma and our sigma star. Because they're not involved in a bond, right? They basically cancel each other out. That's a bit of a, but that's just fine for what we're doing here, okay? Remember, one of the important points I want to tell you guys about is that drawing a Lewis structure is extremely valuable. You get a lot of information out of it, okay? That information is based off of a shortcut though, right? Using an MO diagram gives us a lot of valuable information, but it doesn't necessarily tell us the true story of how things are put together either, right? All I'm saying is each of these have limitations, but together they help us paint a more complete idea of what's going on in the structure. Okay? And I'll give you an example here in just a second of how we can, or what that means. But great, so there that is. Yeah.
So can we like always use like Lewis structures to like check them? Or will it not? Like,
That's what I'm about to give you an example, then I'll answer that, right? The answer is most of the time, yes. Right? Most of the time, yes. All right. So I'm really gonna change things up for you guys. You ready? So a drastically different molecule. So instead of carbon monoxide, you guys come up with nitrogen monoxide. And see what happens. Not at all. Trying. I don't know. We, if you go to like student services, they can get you like a note taker and use a tool to try and run it over. That's if that's something that you need. Go to chat with them. Jennifer should be able to chat. Yeah, but yeah, go take care of that. And if you need a hand with that, just let me know. I mean, I wasn't making a joke, but but you get the point.
Does that have a charge?
Nope. Why do you have to fill in your time? You don't technically have to, right? But for our purposes, it helps us kind of see that both ends of what we, each of the atoms contribute electrons to this is what this. All you really need is your valence line, right? And then fill those in. So either way's fine. Ooh, what's unusual about this one?
There's an odd number.
Yeah. So 5 electrons in my nitrogen, right? Six in my oxygen. Gross. What's weird about this? 11. Not too often have we run into something like this, right? How does that change anything for what we're doing? It doesn't, right? I didn't ask you guys to draw the Lewis structure. I just said just fill in the MO diagram, right? Okay, well, we got 11. Let's do it, right? Start at the bottom. 2, 4, 6, 7, 8, 9, 10, 11. Not too bad, right? Pretty simple to look through these. Right? What does this tell us though now? All right, so the same assessment here, right? We make a sigma bond that gets broken, right? We make another sigma bond, does this one get negated or broken? No, so should we have a sigma bond in here? Not a big shocker, right, that we should have that there, right? So we make a sigma, we make 2 of our pi bonds, but what's our bond order at the end of this?
2.5.
Yeah, so remember our bond order we've got an equation here for us, so I think it's on one of the following slides, right? So basically just using this equation here, right, our bonding electrons minus our anti-bonding electrons, okay, divided by 2. So let's count our bonding and our anti-bonding. So we've got 2, 4, 6, 8, right? 8 bonding minus 3 anti-bonding divided by 2, so a bond order of 2.5. Okay. Now I want you guys to draw the Lewis structure for this. Go ahead and draw me 2.5 bonds. Yeah.
Sorry, where'd you get the 8 from?
Oh, bonding electrons. So 2, 4, 6, 8.
Okay.
The stuff that's not in these star orbitals. Okay. 2, 4, 6, 8. How do you draw half of a bond? Well, stop the bond halfway in between the atoms, right? There's really no way to draw 2.5 bonds. That's the whole point, right? So the point of this example is that there are times when our Lewis structures can fail in terms of giving us an accurate representation of what's going on. And MO theory steps in and kind of helps explain it. There is an unpaired electron hanging out in one of our pi star orbitals. Okay? Do you guys remember what the name is for these unpaired electrons, what we call them? It's a very 1980s word. What's that?
Unhybridized?
Hmm?
Unhybridized?
So hang on, I'm going to come back to that thought. So the pi bonds are made from unhybridized p orbitals, but an unpaired electron is called a free radical, right? A free radical, right? Yeah. Free radicals. Free radicals tend to be extremely reactive. There's something else that we haven't talked about, but MO theory is one of the most important explanations for how things react. Okay? And I can tell from your expressions that you guys want to know more about it. Right? And if you come take my bioinorganic class, I'll be happy to explain it to you. MO theory is how we explain why oxygen binds to your hemoglobin. And not only why it binds, but how it binds. In what direction and what orientation and how it impacts your hemoglobin, all these kind of things. MO theory is an extremely powerful theory. But, as is the theme for this class, when will we see it next? In a different class, right? So remember, the point I'm trying to say is we set a lot of foundations here in Gen Chem, especially Gen Chem 1. You guys will see this stuff again. The unfortunate part is it takes a couple semesters before we can come back to it. Okay? But MO theory is extremely important. It helps us to be able to describe things like radicals and where those electrons are. It helps us to describe why things are reactive. Okay? But it doesn't give us the picture of how the atoms are bound together. Okay? That's its limitation. Lewis structures tell us exactly how things are bound together, and the geometries and the angles and all this kind of stuff. MO theory doesn't do that for us. It tells us where the electrons live, whether they're living in between the atoms in sigma bonds or in pi bonds above and below in the hamburger orbitals, right? Not the bun orbitals, I should say, right? And so each one of these has a purpose, and both of these together help us to paint a complete picture of what the shape is and how it reacts, right? So it's not necessarily just one or the other, it's kind of both of them. What's up?
The pi bonds are the ones on the outside.
Yep.
Or MO pictures have them on the inside. Is that just a design choice?
So it's a, wait, have what on the inside?
The pi bonds, I thought those were the.
They're on the outside, yeah.
But pi ones are on the inside in this picture. Okay.
In what picture?
Your MO.
Oh, no. The orbital themselves and with respect to the, here, I'll show you. There. That's what I'm talking about, right? Pi bonds are living above and below the plane of the atoms themselves. It doesn't, I'm not talking about necessarily just the representation of the MO diagram. I'm talking about the physical location of the atoms.
Okay.
That's what I mean with it, okay?
Thank you.
Cool. All right. So I told you I was going to come back and ask you guys a question about something important, right? About unhybridized p orbitals. Yes. What does it mean to be an unhybridized p orbital? Well, Dr. H, that's when you have a p orbital and it's not hybridized. Nailed it, right? Where do we see unhybridized p orbitals? What geometries? What geometries do we see unhybridized p orbitals?
Definitely octahedral, right?
No. Unhybridized p orbitals. Unhybridized. How many p orbitals do we have? 3. Which one of these geometries, which one of these hybridizations don't need all 3 p orbitals? Why linear? Well, it only takes what? An S and a P. How many unhybridized p orbitals are there in a linear geometry? 2. What's the geometry of carbon monoxide? Linear. How many pi bonds did it form? 2. How many unhybridized p orbitals did it have again? 2. That's got to be a coincidence, right? It's got to be a coincidence that the amount of unhybridized p orbitals correspond to how many pi bonds you can make. I'm just kidding. That's exactly how it works, right? Okay? The amount of unhybridized p orbitals you can make corresponds to, excuse me, the amount of pi bonds you can make corresponds to how many unhybridized p orbitals. Okay? Pi bonds only form from p orbitals. So you have to have those unhybridized orbitals around, otherwise you can't form. Everybody following along with this? Yes. Okay, so linear, you can make 2 pi bonds. What other geometry doesn't take all 3 p orbitals? Trigonal planar, it only takes what? 2 of them. So how many unhybridized p orbitals do we have in trigonal planar? 1. How many pi bonds can you see in trigonal planar? 1. Got it? Do you guys get the very important point I'm making here? Here's my very important point. How many pi bonds will you see in a tetrahedral geometry? 0, unless, what? You can violate, the only exception is when you can violate the octet. Okay? So carbon in a tetrahedral geometry, don't put any pi bonds to it, okay? You guys with me on this? Cool. All right. So very important slide here. Make sure you guys, you got all that down. And that was basically all that I needed to chat with you guys about for this MO theory stuff. Right? Here's kind of the representations of what we've been talking about there. Sigma bonds in between, pi bonds above and below, to the front or to the back, right? Unhybridized p orbitals, your geometries, your angles, your polarity, your dipoles, your partial positives and negatives, electronegativity. Woof! How much stuff did we go through in these 2 or 3 chapters here? A lot, right? A lot. It all comes back to being able to draw our structures, right? And now what we've added onto it is being able to interpret sigma versus pi bonds, okay? Good? Now I know, because I can read your guys' minds, okay? What you guys are thinking is, I want to do another chapter that's all based off of math. Okay, let's do that then. All right. I did. Sorry, I'm getting some interference. All right, so the last chapter that we're going to be dealing with here, right, is about our gas laws, all right? Now, much like chapter 5, which was our thermodynamics chapter, this chapter here is really going to be based off of one equation, okay? The ideal gas law. And we'll talk about that, and we'll kind of construct it and build it up when we get there, okay? But much like our thermodynamics chapter there, that's really the equation that you guys need to start out with. And that's going to help us to be able to figure out and calculate and do what we need to do with our gas laws, right? It's going to get a little bit tricky. It's going to have, chapter 10 has these types of problems that, you know, they turn into paragraphs almost. And they're like, oh, this gas mixes with this, at this pressure, at this temperature, and blah, blah. And they give you a lot of information. But at the end of the day, what you need to do when you start the problems here in chapter 10 is you need to start to just draw out the information that you guys need. Write out your given information. Organize all the numbers that they give you. And once you do that, then these problems tend to simplify a little bit, okay? So what I'm saying is don't get intimidated by how the questions are being asked. It really just comes back to reading and understanding what each bit of data kind of tells you, right? Other than that, it's just simple math once we can kind of deconstruct everything, right? Okay, so we start the last chapter by kind of thinking back on the first chapter, right? And where we talked about kinetic molecular theory here, right? And some of the things that we learned about gases and liquids and solids and that kind of thing. One of the properties of gases is that they can be compressed. Like, okay, but what are we physically talking about when we compress something, right? Well, gases are zipping around this room, right? But there's a lot of empty space in between the individual molecules. So when we're talking about compressing things, we're just talking about removing that empty space, pushing things closer together, right? It's if I ask you guys all to get up and move into the center of the room here, right? That's all we're talking about. Now, a consequence of this, or one of the things to think about, is that because they're compressible, that means that there's a lot of space in between the molecules themselves. So what does that mean for us? Well, this actually brings in an important idea that we'll bring back in this chapter again a couple times, okay? One of the assumptions that we make is that gases don't interact with each other, okay? And the thought is this: if there's a lot of space in between molecules, those atoms can't really talk to each other. Or excuse me, those molecules can't really talk to each other. How do molecules talk to each other? What are the 3 ways that we learn? Or 4-ish ways? What are our intermolecular forces? Dipoles, right? Dispersion forces are London, our van der Waals forces, right? So dispersion, dipole, and hydrogen bond, right? So if you've got a lot of space in between your molecules, they can't talk to each other, okay? So this is an assumption that we make. It simplifies our math. I think at the end of the slides, or way at the end of the chapter, I'll show you guys how we unsimplify the math, but we'll get to that, okay? Gases expand into any volume available. That's also going to help us for the our math. Because when I ask you a question, we're going to say, this amount of gas was put into a 25-liter container. And so the volume is assumed to be 25 liters, okay? So all I'm saying is treat the volumes of gases the same as you would for a liquid. That's fine, okay? Gases are completely miscible. They instantly mix together is the assumption that we make. And these are going to be the terms that we use: temperature, pressure, volume, and lowercase n. Lowercase n is just moles. As a big shocker, we're going to have to talk about moles again and do conversions, okay? So some of the important ideas are going to be building upon here. All right, when we talk about pressure, right? Pressure is just a measure of force over area. You don't really need to know that. That's a little bit more about the, I guess, the physics side of things, right? But we will be talking about pressure and not of the, psychological kind here, right? Just what it is that we're dealing with. The other important thing is which units are we dealing with, okay? That's one of these things to pay attention to in this chapter. What are the units of the data that is given to you? Is it in atmospheres? Is it in torrs? Is it in millimeters of mercury? Right? Is it in pascals? All these kind of things. Okay. The SI unit is pascals here, but typically we're going to be hanging out in this down here. in atmospheres or torrs or millimeters of mercury, okay? Atmospheres is maybe a little bit more tangible for us, right? Right now we're sitting at about 1 atmosphere of pressure at sea level, right? Give or take, okay? So atmospheres might be the thing that you're most comfortable with or understanding, but just pay attention to those is what it comes down to. Right, so here's what we talked about before, adding a couple of things to it. You guys definitely don't have to write all this down. These are the assumptions that we make when we're dealing and calculating things with gases, right? Something that's new is elastic collisions. That means these things just bounce off of each other, okay? For those of you guys who have taken physics or will take physics, you'll talk about the mathematics involved with what happens with elastic and inelastic collisions, okay? But they don't slow down, they have small attraction or repulsive forces from each other, very high speeds, completely mixed. Make math happen. That's what this slide is talking about, okay? Right, we're gonna be talking about energy and the energy of the motion, that kind of thing, that's fine, right? The average energy is proportional to temperature. That's not something new, right? We've been talking about this all along, and especially in chapter 5, where we said, hey, if I'm heating something up, where in the world does that energy go to begin with, right? It goes into the motion of the molecules, whether they're physically moving around, zipping around, or whether they're bending or stretching or any of these other kind of things that might happen with these molecules, okay? And so as we add temperature here, right, as we increase the temperature of a gas, we just see that the average speed increases for things. Energy has to go somewhere. That's all I'm showing you with this, okay? The higher the temperature, the higher the speed. Now, why in the world am I telling you this? So we're about to introduce a couple of equations, okay? And these equations have different variables. And what would be useful is if we could kind of think about and visualize what's going on with these things, okay? And what I mean is this. So as I increase the temperature for a gas, it's moving around and zipping around at a higher speed, okay? It's like, okay, that's fine, that's what the graph shows. Now imagine that this gas is trapped in a container, okay? A sealed container. And I start to heat it up. Do the molecules still move faster? Sure. Do they still bounce around more? Sure. What are they hitting into? Well, the side of the container. Right? And if I add enough energy into that container, into that gas, what's going to happen? What happens when you heat a sealed container? It explodes, right? Well, why does it explode? Well, we're increasing the pressure, and pressure is what? Force over area, right? So when you're feeling pressure, when you're thinking about this, right, it's basically the impact of these molecules onto the end of the container, right? Onto the boundaries of the container. So they're basically smacking into that is what it is, okay? So one of these ideas to think about is the relationship between pressure and temperature, okay? And volume and temperature, and moles and temperature, okay? This is all gonna come together into one equation for us is what it is, okay? Another idea, the lower the mass, the higher the speed, okay? The smaller you are, the faster you move. There you go. That's all it's talking about here, okay? And so this has implications in things like diffusion, okay? So you guys have all had a helium balloon, right, at some point, okay? And on the first day, it's great, it's fun, you can, right, it's sitting there and floating. What happens after about day 3? Right? Basically deflated itself. Why? Does the helium magically decompose into something else? No, right? It passes through the container of the balloon that it's in, right? If you happen to put a heavier gas into that, it would deflate slower, okay? So the mass of this relates to the speed, and that can relate to the diffusion of a gas across a membrane, like the balloon or something like that, okay? That's pretty darn important for things like our lungs that give us oxygen to breathe, right? Diffusion, pretty darn important. But anyway, there's a relationship that we can think about here, right? The escape of a gas through tiny holes into a vacuum, right? there's a, diffusion rate is proportional to, so that little weird looking halfway, 8 infinity symbol there, that just means proportional to, okay? So the diffusion rate is proportional 1 over the square root, right, of m, where m is the mass. Not too bad, right? So a simple question is, what's the relative diffusion rates for these two gases here? And you just do a relationship of the two molar masses for those things there. Helium's 4 and nitrogen's 28, right? So. Right? Not too bad, right? So, now that we kind of understand that, the last thing that I need to define to you guys is what do we mean by an ideal gas? Okay? So any equation that relates volume, pressure, temperature, and moles is a gas law. We're going to learn 4 gas laws? Yeah. Yes. Okay. Most gases at room temperature and pressure are ideal. They follow a simple set. Okay. That means that there's a characteristic that they all follow. That's all we're saying with that. And that allows us to model them mathematically using our ideal gas law. That's all it's saying. One important thing that's unique to this chapter. So all of our temperatures have to be in Kelvin. Okay? They have to be in Kelvin. Why? What's so special about Kelvin? 2 things that are special about it.
It's the SI temperature.
Hmm?
The SI temperature.
That's true.
It's how atoms do.
Mathematically, what's important about Kelvin?
0 is no more movement.
Well, 0 is practically not achievable, right? And the other thing is there are no negative values in Kelvin, right? Kelvin is only a positive scale, and for all intents and purposes, it'll never get to 0. Okay, and that's important because we're going to be dividing by temperature in a lot of cases. What happens when you divide by 0? Nothing, right? You can't, right? You can't divide by 0. So, but can we easily get to 0 degrees Celsius? Sure. Can we easily get to 0 degrees Fahrenheit? Absolutely, right? But we're never going to be dealing with a case, and gases certainly don't behave ideally at 0 degrees Kelvin, okay? So to simplify the math, we're going to be doing everything in Kelvin. So don't forget to do your conversions if you guys need to with that. Okay? Cool. All right, so this seems like a good place to kind of pause before we launch into kind of the rest of the meat for the gas laws chapter there. So I will see you guys on Friday, right? Please go watch the aerodiagram lecture.